My name is Guy Royse. I'm a developer advocate with Redis. This talk has absolutely nothing to do with Redis. It's just because I like it. So, but buy more Redis. It's free. If you want to follow what I do, I have a Twitter account at Twitter at Guy Royse. The thing that really matters on this slide here is the GitHub URL. I have all this code out there in a GitHub repository, so if you want to play around with the deep learning like a Viking, you want to classify some runes using convolutional neural networks and Keras, you can run the same code and even use the same data that I created to do it, and you too can have a model overfit to my handwriting. And if you want to read a blog post from 3 years ago, you can go to my website at guy.dev. This is a very important qualification. Anyone have any idea what it stands for? I am not a data scientist. Correct. So this is a data science talk for developers by a developer. So I have learned a fair bit about how neural networks work. I've got an intuitive sense, but I'm not particularly mathy. So I try to explain that intuitive sense of them, and a little bit of the math is of an algebra level. But there's a bunch of calculus for training these things that honestly I don't understand, and but I don't have to understand in order to build them. And so you can use the tools without knowing the math. Knowing the math is always great, just like you can program in TypeScript without knowing JavaScript, but really the JavaScript helps. I'm not a data scientist. However, I am an enormous fan of Vikings and Viking culture and things Viking. I think that's probably because of my Viking heritage. I went out and did the 23andMe and got my results, and turns out I'm Viking. Who'd have thought it, right? And so that's always given me kind of an interest in Vikings. And runes, Vikings are kind of metal, aren't they? They're kind of badass. The Vikings, when they would communicate, when they would bother to write things down, they used an alphabet called the Younger Futhark. The Younger Futhark is called the Futhark because the first 6 letters spell the word Futhark. Just like our alphabet is alpha, beta. So same idea. And so you've got F, U, T, H. I love that the Viking alphabet starts with F, U. It's like the most Viking thing ever, right? No, that's our stuff. And then you got Thorn, or Thurs, which is TH, and then URK, or ARK, sorry. And so it's just an alphabet, just like ours. There's only 16 characters, so it's a little limited. Like they don't have a G, they don't have an O. And so if we take my name and turn it into into the Younger Futhark, it comes out as Kai Rice instead of Guy Royse. So it's a little limited, but it was good enough for Old Norse. It's called the Younger Futhark because there was an alphabet that preceded it that was called the Elder Futhark. You was going for older, weren't you? Yeah. No, we got to use epic-sounding words like elder, like the elder race of man, you know, like in 2112 with Rush. So it's called the Younger Futhark. This is their alphabet they used. Works just like ours, but slightly different. And we know about it because they carved it into lots of things. There's these rune stones all over Sweden and Norway that are full of these runes. And if you just look at this picture, right? It's got like dragons and a big like iron cross on it. It looks like Lemmy and Motorhead are going to step on stage, right? It's just kind of metal, and it's got these cool-looking symbols all around it. And but it's actually kind of sweet what's on here. This is a monument to well, I'll just read it here. Danner and Huskarl and Sven and Holmfrother, the mother and her sons, had this stone erected in memory of Halfdan, the father of Danner and his brothers, and Holmfrother in memory of her husband. So it's a memorial. Kind of cool, actually. And if you look closely at it, you can actually see the runes on it. Right? These characters right here, that's the name Holmfrother. And so those are the characters for it. So it's a real thing, right? There's real words on here. Kind of cool. And you are using runes too. You have runes on your phone right now. I don't mean the Unicode, because those are there too. But your Bluetooth logo. Does anyone know why it's called Bluetooth? I bet you someone in the audience does. Harald Bluetooth, that's right. Bluetooth was the code name for this project to connect all these devices and unite them together. And so they use it as a code name because Herald Bluetooth united the various kingdoms, i.e. conquered, and brought them together. And so the Bluetooth logo is a overlaying of his initials. Well, his first initial of his first name and his nickname, Herald Bluetooth. So that first rune there is haggle, and it makes the H sound. And this is Bjork, which makes the B sound. And we overlaid them, or someone overlaid them, and made what's called a bind rune, which is the magic object that's in all of our devices now. It's just called a bind rune when you put them together, but it sounds like a bind rune sounds like a magic spell. Like it's like we're going to contain a demon with a bind rune, right? No, it just means we've laid them over together. Looking at the Younger Futhark, you might notice that some of the letters look familiar. Like that Bjork looks a lot like a B if I carved it. And that's not a coincidence. If you look here, you look at several letters and you compare them to Latin and Greek letters, there's a lot of similarities. My favorite is Isa, which is the I sound. Turns out no one changes how they draw a line. Just a line. But over here you got Bjork and Tyr, right? And so these are clearly, it's Tyr, P, and Tau. You got Bjork, B, and Bravo. You look over here, you got Logger, L, and Lambda. Wreath, the R sound, R and Rho. And so there's a lot of similarities here. There's that FU again. And that's not a coincidence. It turns out that all these languages, these character systems are related. I realize this has nothing to do with convolutional neural networks. I just think it's cool. And so thank you for being patient with me. And so the Younger Futhark came from the Elder Futhark, which came from Etruscan. They're not sure how it got from the Etruscans or to the northern Germanic tribes that started using the Elder Futhark, but it did. It might have been through an Italic alphabet. It might have been through Etruscan directly. They're not sure. They don't have enough pieces of evidence to figure it out. But it came from there. The Etruscans got their letters from the Greeks. And the Greeks got their letters from where? The Phoenicians. The Phoenicians were the Proto-Canaanites. They were the language of the Proto-Canaanite. But the Canaanites, you might remember them from the Old Testament. And they got it, along with a bunch of other Semitic tribes in that area, from the Egyptians, probably. And so they took hieroglyphics and simplified them and said, well, this one is this sound and this one is this sound, and made it the first alphabet. And then that forked off, and that created the Latin alphabet, created the modern Latin alphabet that we use today. Various forks of this have created alphabets all across the world, all the way into India. Mongolian uses this alphabet, used to. So that one invention of hieroglyphics turned into this, it just forked and evolved over the millennia. Really cool. What we want to do is we want to build a neural network. Use some AI, use some machine learning to take handwritten runes and recognize them. So we want to take haggle here, and when I write it with my hand, and turn it into, hey, this is the rune haggle. That's the project we're working on today. And we're going to do it with neural networks. So this is the part where I say, I am not a data scientist, so there are probably subtle details where I'm wrong, but the broad strokes are good. A neural network you can think of as, I like to think of them as just functions. Like in the mathematical sense. I put in a bunch of values for x, I put in a value for x, I get a value for y out. I put in lots of values for x, I get a value for y out. A neural network takes that, if you got an x coming in, you got a y going out, what's that going to do when you plot it? Draw a line. Neural networks do that in more dimensions than 2. So if we have like a single output and 5 inputs, then we have 6 dimensions. And so we're drawing a 5-dimensional line, a hyperplane, through a 6-dimensional space or a hyperspace. But we can think of these in 2-dimensional aspects just because it's easier to think about. But they're basically taking a two-dimensional plane or a three-dimensional space and bisecting it with a plane or a line, like this. So we draw this line separating this space, and then we can use that to classify things. If it's on one side of the line, then we know it's one thing. It's a hot dog. If it's on the other side of the line, it's not a hot dog. And if you want to classify multiple things, you can have multiple lines, one for each thing, and you can just through process of elimination saying, well, it's not a hot dog, and it's not a wiener dog, and it's not a cat, and it's not a hamster. So what is it? And so you can eliminate and find out which side of the lines it comes in. The other thing you can do with this is you can look at how far away your point is from that line that represents that division. The further away from that line that you are, from that hyperplane, the more sure you are that you're in the right category. The closer you are, the less certain you are. So you can get a score by measuring just how far away it is. Just measure how far away it is from the line. The other thing you can do with these lines is you can predict numbers. So here's a very simple model that determines the number of oarsmen required for a ship versus the size of the ship. And this is actually just a plot of the ReLU function, but I'm reusing my graphics. But it works fairly well here because if you think that the x-axis is the size of the ship, I can then say, well, what's the size of my ship in tons? Negative isn't going to be valid. You don't need any oarsmen to row a ship that's negative, so that's a correct answer. And as the ship gets bigger, the line goes up. So you can use these numbers that they predict. You can put in an x, the size of the ship, get a y out by finding out where it intersects that line. And so neural networks can draw these lines that we can use to predict numbers or to categorize things. Neural networks, of course, are made up of neurons. Neurons are functions. They draw lines, just like the neural network does. They have multiple inputs for x, and they give you out a y. So this one is a three-dimensional hyperplane bisecting a four-dimensional space because there's three inputs and an output. To understand how a neuron works, let's look at the simplest neuron, one that just takes a single input and gives out a single output, because these are easy to plot on a piece of paper and to think about. Inside of that neuron, which is a function, we have weight represented by the letter W and a bias represented by the letter B. And what we do is we take the weight times the input, so x times W, we add the bias, and then we get a value for y. So this is the math that's happening inside of a neuron. Anyone recognize this? Anyone recognize this? Yeah. So that neuron draws a straight line. And so you can take these neurons and get different lines and then feed them into other neurons and get other lines. But if you take a bunch of layers of neurons and feed one into the other, and they all generate straight lines, you're going to get a straight line. But our classification problems might not need straight lines. We might need to have lines that move around and curve and twist and weave, because our problem is probably more complex than something we can solve with just a linear function. If we can solve it with a linear function, we probably don't need a neural network. We probably need Excel. And so by default, of course, you get this nice linear function. But so what you can do to make that line less linear, to make it less liney, is you can use an activation function. An activation function is a function in our function, which is in the neural network of functions. So it's just functions all the way down. And the activation function takes the value that you compute for y and transforms it before you return it. And there are a few options here. The original one, with the perceptron when neural networks were brand new, was the step function. It basically said, if I've got a positive number, it's 1. If I have 0 or negative, it's 0. And so the idea here was that it was like getting past a threshold to fire the neuron. Like if it got enough value in there, it would finally trigger. And it's almost like a logic gate. You're taking analog floating point values in, and then you're spitting out either a 0 or a 1. And I mean, you can use it. No one's really using it for much anymore that I'm aware of. But it didn't provide any subtlety, right? It was either on or it's off. It was triggered, not triggered. And so people started playing with some other functions. By the way, this is the reason it's called an activation function, is because does the neuron activate or not? The function would determine whether it would activate or not. But they soon got more sophisticated. We used a sigmoid for a while, and that would give us a value from 0 to 1. But smooth it out, so we get a little bit of gradation. So that neurons could fire, but they could vary their strength and how hard they fire and influence future neurons. Some used hyperbolic tangents because they wanted to have negative numbers. They could have neurons that would suppress the output of neurons by returning negative numbers. So you could use a hyperbolic tangent. It's basically a tall sigmoid. And this is what most people are using for, and this is what I use in my examples, is rectified linear units. This is a nice, quick, easy algorithm. It basically says if it's 0 or more, it's what it is. Otherwise, it's 0. So just flatten out all the negative numbers. And this is fast and easy to implement. There's no, it's a basic, we've written this code before, right? Not complicated. But provides enough variation to actually be able to turn linear functions that go into linear functions. These rectified linear units cascade into each other and can actually create curves. The math for more realistic neurons that have more than one input, which is normally how you do it, is pretty much the same. You're just multiplying every input by every weight and summing them all together, adding the bias. But everything else is the same. So this neuron here has 4 dimensions instead of just 2. And so the math looks like this. The weight, the input, x plus the times the weight, plus x times the weight, plus x times the weight, plus the bias, gives you y. Or to use a little bit of summation. By the way, sigma is soul in the Younger Futhark. It's the little fancy KISS-style S that they use. So this is pretty much all the math in the talk. So nothing super hard. And then your neural network takes all these inputs, draws these lines, and can make predictions, make inferences. But this type of neural network, this is a fully connected neural network. Each of the layers connects fully to the next layer. So all of our inputs connect completely to the next layer, and all those layers connect fully to the next layer, so every combination is connected. They're actually bad at recognizing runes or any kind of image classification. And this is because sometimes I will draw my rune, like mather makes the M sound. It's the one that looks like this, right? It's like the tree. I think it's supposed to be a person doing this, right? And because sometimes that rune might be to the left of the image, and sometimes it might be over to the right of the image. And sometimes the arms might not be exactly straight, and sometimes it's a little short, and sometimes it's really tall. And a conventional neural network isn't looking at that sort of pattern. It's just sort of memorizing every possible version of it. So they need to be big to do that. It's like I could recognize you, Joel, if I looked at you front on from the same distance. But if I stepped back 50 feet, you'd be smaller and I couldn't recognize you. I'd have to memorize how you look that way as well. And then I have to memorize what you look like from the side and from lots of different angles. And memorizing all that is, well, impractical. And so neural networks are actually bad at doing image classification. But there's convolutional neural networks, which is a special variety of neural networks which are great at it. Well, they're good at it. So this is a convolutional neural network. And thank you for attending my talk. I'm going to go into what all these little pieces mean. There is a more complex way to show this with the relationships, but it's hyperdimensional. It's got lots of dimensions. It's hard to visualize. Frankly, I haven't fully intuited it, but the individual pieces make sense. I just don't have a good picture showing how everything's connected from a graph point of view. The first trick of a convolutional neural network is it has, well, convolutions. Convolutions are ways of passing over the image to identify, is this part of the image like a thing that I know about? And so you've got these things that you know about, patterns within the image, lines and shapes and those sorts of things, that are called filters or kernels. And so you take the input image. Here we've got a 24 by 24 bit input of Mather. And we've got filters where we've got, like, this first filter here is line straight up and down. This one's a big plus. This one's, diagonal lines, right? And it's panning across the image and saying, where does this match? And if it matches, then we mark it as matching. And if it doesn't match, we don't mark it as matching. So I've got animation here that shows this idea as we patiently watch for it to go by. So it's scanning and panning and scanning across the image, and it's looking at the filter and saying, does it match this or not? If it matches the pattern, it writes, it puts a 1 there. It marks it there. So we're going to, next row, we'll get a hit. Right there. It matches with the filter perfectly. Right there. And so this gives us an output, a convolution, that is a map of everywhere in the image that this shape was detected. And you can cascade these. So I can do convolutions on the output of this, and then say, and it creates a hierarchical decomposition of the image. So these filters, which are trained through back propagation through the neural network, learn how to detect different lines, and then shapes from those lines, and then letters from those shapes. So it creates a natural hierarchy. It discovers the hierarchy when you train it, which is kind of cool. And these aren't actually happening against, binary values. I've got numbers in here to show you the math that's happening. And so here we've got the same formula I was showing you earlier. That's sum of the inputs times the weights plus the bias. And so here, the weights are the filter. They're the kernel. And the inputs are the portions of the convolution. And then the output, the y's, are plotted into this grid here. So if we look at this, we can look at right here at the very top. Let's look at the top left. We got all zeros and a 1. We take x's times w's. All those zeros equal 0. 1 times -1 is -1. And so we add that all together, we get -1. We add the bias, that gives us -2. We apply the activation function and say, is it greater than 0? It is not. So this has a 0. So we put a 0 in the top left corner of the output. If we look in the middle, well, 1 row down here, we've got a bunch of zeros and 2 1s in the middle. And so if we do the math on that, we end up with 1 times 1 is 1, 1 times 1 is 1, so that's 2. We subtract 1, we have 1. Relu function spits out a 1. And so we put a 1 over here in that spot. So far, so good? So this is that same linear function that's happening here. Once we have these convolutions, we can do a process called pooling, where we, in essence, sort of concentrate them down. So here we've got a 9 by 9 output of our, however wide that is. I think it's 16 by 16. So we've got a 9 by 9 output as a result of that convolution, and we want to pool it into something that's 3 by 3. We're going to take 3 by 3 chunks out of this and pool it down, compress it down. And so what we're doing here is we're looking at each 3 by 3 grid on here, starting from the top left, and saying, is there something in here? If there is, then we translate it to the pooled output. It's kind of like squinting. Like if I drew the rune Mather and this was slightly crooked, does that really matter? No. And the pooling will cause it to basically say, well, if it's close, we'll count it. It's sort of finding things that are nearby and saying that's close enough. So here's how this works with fancy animation. And it goes through and says, hey, there's something there. And then it goes through, oh, hey, there's something there. And so this output from the convolution is a map of all the times that like a particular shape was detected. And now we've concentrated that down and saying these shapes were close enough to each other. And again, this is happening with numbers. What's really happening here is we're looking at each 3x3 area and saying what's the maximum value in there. So in our previous example, we ended up with this pattern here with a little 1 up there and then 2, 2, 1 down here. And we pool that, our top left corner here is just 0 because it's all zeros. The top middle quadrant, it's sextant. What would you call a subdivision of 6? Or 9. Anyhow, the max number there's 1. Down here on the bottom center, the max number is 2, etc. So you're just taking those 3x3 chunks and taking the max number. So, like squinting. Once we've done that, we can take the output of that pooling, and we can just flatten it out to conventional little neurons. And then those neurons can be fed into a fully connected network, and then we'll get inferences out. And that is convolutional neural networks in 30 minutes. Actually, about 15, because I spent 15 minutes talking about runes. But let's be honest, that's probably the most valuable thing you learned all week, right? Thank you. So. I don't remember why this photo's in here, but I think it looks cool, so I'm going to leave it. Let's look at the next thing. So I have built something to do this thing that I'm talking about. So we're actually going to we're going to make this real. I use Keras to do it. If you've never used Keras, it's a domain-specific language that makes writing neural networks easy for developers like me who don't understand calculus. I can just compose and say, I want to build a neural network that has a layer of this type. Here's all the configuration options. Another layer, here's all the configuration options. And then I just tell it to build it and train it, and it does it. And this is the kind of machine learning that I like to do. It's all in Python. So if you're a Python developer, you're in luck. If you're not a Python developer, you're in luck. You get to learn Python. And it's part of TensorFlow. Wasn't originally. When I put this talk together, actually, it wasn't part of TensorFlow, but it is now. And so if you've got TensorFlow, you can do this. Here is some sample code. It's not actually that complicated to set this neural network up. I create a new model. It's called sequential because it's in sequence. You've got a layer, and then it's followed by a layer, and it's followed by a layer, and it's followed by a layer. And then I just start adding layers to my neural network. I add a 2-dimensional convolution layer to it, which suggests that there might be 1- and 3-dimensional convolutions. I don't know if there's actually a 3-dimensional convolution in TensorFlow. There is a 1-dimensional convolution. We're using 2-dimensional because our pictures are 2-dimensional, right? But if we were to say maybe analyzing sound data over time, and we were looking for like the sound of applause, or the sound of booing, which is much more likely, then we could use a 1-dimensional convolutional network to do that. Because it's all about finding patterns. And then we have the number of kernels, or the number of filters we want, 48. The size of those filters, they're 3x3. Our activation function is relu, which is just like we showed earlier in the code, or on the slide. And my input shape for the images is 24 pixels by 24 pixels. And that 1 at the end is for the color channels. I have 1 because I'm doing just the alpha channel. It's just black and white. But you could have an RGB and an alpha channel. So you could have up to 4 there. Or I suppose if you wanted to do like other weird things, you could. But this is what I'm doing. Then I specify a pooling using the max number, which is the one we talked about in the slide. That pool size is 2 by 2. So it's going to go across the output 2 by 2 and concentrate it down, sort of have it in size. And then we do it again. Another convolution, another pooling. We flatten it. So right there, we just call flatten. That adds a flattening thing. And then we have a dense layer with 128 neurons. Its activation function is also relu, rectified linear units. And then as our final output layer, we have a dense layer with 16 neurons. Any idea why there might be 16 neurons? There are 16 runes, correct. And the activation there is softmax. So these are all going to spit out numbers. Softmax takes all those numbers and then makes them sum to 1 proportionally. So you can treat them as percentages. And then the output neuron that has the highest percentage is the one that's most likely to be the runic We compile it. We give it a loss function. The loss function is the thing that tells us how wrong we are when we get our output. As our data comes out, how incorrect, how far off is this? The optimizer, we're using Atom, is the algorithm used to adjust the weights and biases throughout the neurons, to adjust them based on the output of that loss function. And then the accuracy is just for us humans. And it's just expressed as a percentage. How often were we right? And then we call fit, pass it in some training data. Xtrain is all the runes. Ytrain is the names of all the runes. We go through this in batches of 32, so we do 32 things through it. We apply the loss function, we apply the optimizer, or we compute the loss, we apply the optimizer, and until we're through the data. We go through the entire set of data 20 times, epochs, and verbose 1 says, tell me all about it. Let's do a demo. Let's see that this is real. Okay. Can you all see my screen? Is it big enough? Okay. This is for later. Okay. So I have, in here, I have written a little app, and I've got these JSON files that are full of runes. I actually spent an entire 8-hour day at work drawing runes in a little app I wrote so that I could get test data, or get data to train this. Probably the most unusual thing I've ever been paid to do. And so that's my input data. I've got this little build model.py, and it just goes through and loops over that data. Let's go ahead and pull this down so you can see it. Just loops through all the files in that directory, turns them into NumPy arrays. I like to call it NumPy. I know it's NumPy, but NumPy's funny. And they're values from 0 to 255, but I need them to be floats, so we do a division by 255 here to get between 0 and 1. Got our label encoder here. This is just getting our data ready. Here we're splitting our data out. We're taking 80% of our data to train the model, and we're setting 20 aside to test it, validate that our model's there. We don't want it memorizing all the answers, cramming for the test. We want it to learn the pattern of things. And then here's all the code that you saw on the slides, where I'm creating a sequential model, adding the convolutions and the pooling, flattening, dense, and then I compile, and I spit out a little summary, and I call it. So let's build this model. Okay. So Conda, I'm using Anaconda, activate Viking. Perhaps activate the Vikings. That goes over better in Minnesota. So now I've got an environment that actually has all the tools I need, and so I can do Python, better than the other typo that you do for Python. How many people have done that one? The Python. There's actually a website called python.org. Go there on your own. So Python, and then build model.py. And this will take a moment to kick off, and then it'll blur by really quick. There we go. Model built. Pretty quick. And if we scroll through here, we can see that I went through all my files here. Obviously, I used UUIDs for my file names. And then it comes in here, gives me a warning about something I don't care about. Probably that I'm not using a C-compiled version of Python, or of TensorFlow and everything. And then here's sort of a summary of my model. And then here's it going through training. So the first run through epoch 1, not very accurate. High loss. And you can see as we go by, it gets pretty accurate. It's a little too accurate. Pulls back. My accuracy is in the high 90s. This model's probably overfit to be that accurate. And then I save off the model files. There's a JSON file that represents the structure of the neural network, and an H5 file which stores all the weights and values, biases that are in the neural network. So we look at the, actually, I don't know if I showed you one of these data files. You click on it, you can see it's like rune, and then the name of the rune, and then data. And it's just a two-dimensional array. I can side scroll here. It's not letting me. But it's a two-dimensional array with 0 through 255 in it. So we've got a model. Let's go ahead and do Python app.py. I'm going to go ahead and kick off the app. Now, app.py is it's just a little Flask app. It's got some endpoints. One of them is for saving off new models. One of them is for just pointing to a static directory with a bunch of JavaScript code, which you don't want to see. Believe me, I'm not proud of it. And one of them is an endpoint that allows you to classify. So you can submit a drawn rune, the data for one, the JSON for one, and then it will respond back with what it's using the model. So here I'm loading the model from JSON, and I'm loading the weights. And let's look at my save rune. So you can see more code. And so here's detect. And so this is transforming the data, converting it to NumPy, and then we're calling model.predict, passing in our image. And model.predict wants an array of images. I'm just giving it one, so we need to get the first element. So let's see if this works. So here's the little app that I wrote. To enter data, I just draw the rune. It's prompting me that, and I hit save, and it saves it off the disk. This is how I spend an entire day doing that. But it will also detect runes. Can I get I'll do one, but I think it'd be more fun if I get a volunteer from the audience. Does anyone want to do this? Come on up. All right. You look suitably Viking-esque. Well, don't worry, so did I. So maybe they'll match.
Oh, yeah, it'll work. Right.
So it's actually pretty simple. You go there and you click and you drag to draw what you want to do. When you are happy with what you've drawn, you can do any rune you want.
Oh.
The R is just so that when you create data, okay, let's see. Go ahead and click detect. Let's see what it does. And click it.
I don't know back. I don't know how to do this.
You just it actually the whole thing like presses in. So it actually, I'm surprised actually. It figured it out. It figured out Ryan's crappy handwriting. Thank you very much, Ryan. I'm actually surprised. I thought this might identify it as Quan because these are so blurred together. I wonder if I fill this in, if it'll detect as that. Oh, no, it still figures it out. Yeah. It actually is visual, and so I'm storing all the bytes here, and then every single time you hit detect, I go through the little canvas that I'm drawing on and read all the image. It's actually a HTML5 canvas that we're drawing on, and I just pull all the alpha value out of all the channels. So, and yeah, it works pretty well. See if it'll do that. Did not do well on that at all. I did not give it good data that spanned all the edges. When I did this, I tended to draw them all in the middle. So it's not the best data to train it with. But all the data is out on GitHub, so you're welcome to add to it. Let's see if it can recognize Herald Bluetooth. So let's put haggle in here. Did great. See if it'll do Bjork. Let's do Wreath first. See, sometimes, yeah. You can see why it did that, right? It's because it's stupid. It's only as good as its creator. But we should be able to put the Bluetooth logo in here. Let's see what it does with the Bluetooth logo. It's not the Bluetooth logo. That is the bind rune. We're going to bind the demons inside of this model. That's what it detected it as. It's a reasonable guess. I mean, it's the haggle as opposed to the Bjork. It's going to be one of those, right? One of the things I think is kind of fun about this is if I maximize this, I spit out the results. That's the actual data that's coming in. So we hit the URL rune detect. It spits out that array. And then here is the outputs. This isn't the softmax. It's when I spit it over to categorical. You notice there's a 1 here in position 5, or 4 if you're 0-based, which is haggle. So it did what it did. Let's do one more rune. Probably make him a proper Viking. There we go. I know they didn't have horns on their helmet. There's always one. We detected that as all that work. So yeah, so this is my silly demo. Thank you. Let's head back to the slides. So here's a big pile of resources that I used in putting this together a few years ago. They should be fairly current still. I had some Microsoft CNTK stuff in there that I didn't do anymore, but lots of resources to go check out. All of this is up on GitHub at this URL. So if you want to play with it, github.com/GuyRoyse, deep learning like a Viking. I normally have a QR code here and make a joke about how it's perfectly safe to scan it, and that the QR code will never give you up nor let you down. But I did not put that in this one. So this is the URL. The slides are up there and everything. So I'll leave that as I stall, and you all take photos. I don't know what my next slide actually is, so. Yeah. I don't remember, honestly, if I built it to do that. I mean, you can get a confidence level out of these things. So normally what'll happen, like if the output of the neural network will be a bunch of percentages. And so you would have 16 percentages, and one would be really, really big, and the other ones would be low. And so you can, I don't know how it's computed, but that would give you, if they're all like, well, this one won by 2%, then it's not going to be very sure. Whereas if this one won by 90%, it's probably pretty sure. So you could approximate something that way. I know there are ways of computing confidence levels, like when you're using a line with a binary classifier, your confidence level is how far away it is from that line. If you're really close to the line, you're not very confident. If you're really far from the line, you're very confident. And so those things are available. Honestly, it's been so long since I put this together, I don't remember. So here's a bunch of pictures I stole off the internet, making this talk. And I guess the rest of my slides were that's it. So thanks a lot. I've got time for like 2 more questions maybe. Yeah. I don't know that I even put a license on it, but if I did, it's probably MIT. So have at it. Yeah, so it's as open source as it gets. It's probably public domain. So. It gives you the hierarchy. So the first set of filters is going to be learning the really simple shapes like line, and the next layer of filters are going to be learning things like, it's looking at, you end up with outputs that show where all the lines are at. And so then you want to say, well, given that I have a line here, here, and here, that means I have this shape. And so they're basically layers of the hierarchy as you break the thing down visually and hierarchically. So you start out with lines, you get shapes, and like if you're doing faces, then you start getting, the shapes start turning into like eyes and noses, and then they start composing into faces. And actually, if you ever like look at the filters that are created, like you can look at the images through the layers. Like with facial recognition, it's super creepy because it's just pieces of like faces. So that's why there's multiple layers. A lot of what I chose to do for this was trial and error. I poked around and got something that worked fairly well. So some of that's there too. I'm doing letters, which is a fairly simple problem, and so I really just need shapes. I don't need to go much more beyond that. But if I was doing something more complex, I would have used a larger, more layers. And if I was doing something real, I actually wouldn't have even done those lowest layers because there are pre-built lower layers that you can use built on top of that. So you can just like train the specific thing you care about without having to learn lines and shapes and faces and noses. Yeah. That's what I'm talking about. That was the word I was looking for, is transfer learning. I think in this particular case, it's superfluous, and it actually would complicate the demo. So no, I haven't actually, but you could totally do that. And I'm out of time, so thanks a lot, everyone. Thanks for sticking it till the end.